go out to the innervation points of those target neurons and test what happens there. And she hadn't even thought of that because she hadn't arranged the information that way in her mind. So now, if we're going to investigate cognitive architecture, if we call it architecture, I'm just looking at the time, we're okay now. If you're going to call it architecture, let's draw some things, okay? So I did this experiment with my sister. Let's just play with architecture a little bit. And we're talking about cognitive architecture, but let's pretend it's real architecture. This is a real complex, this is what my brain looks like. This is a real complicated architecture of one of our buildings on our campus. The architects produced this by putting all the layers of everything on top of each other, and they can't even read it this way. But I said, we have to do this more simply, because yeah, I agree that's what my brain looks like, but it's not very helpful. So I'm going to ask my sister to draw our house, and just a floor plan. So she drew a floor plan of the house, and she showed where everything, it didn't have to be very accurate, it's just a functional thing, you know. If I had this map in the dark, would I get to the right room and not leave the house and wander down the street or whatever? So she drew this, and then I said, okay, I wonder what a child would do when given this task. She had 2 grandchildren who were 8 years old, so I asked both of them, and they're identical twins, so I had a control, okay? So the first one drew the house like this. This is what I call the octopus house, okay? So the rooms are in the right relative positions to each other. Go back. But they're connected by tubes and strange spaces. And so his identical twin brother, who's more the scientific type, drew this version, which is a little less organic and a little bit more, I don't know. And the same thing happened. So he's got rooms and tubes and I discovered something pretty interesting, and that is I discovered that children, there's 2 fundamental aspects of houses that they don't understand. You can tell what they are, right?
It's not contained within a structure.
So everything has to fit into the shape that's the outside, right? And you can walk around this house and it's a square. And the second rule that they don't know is this wall is the back of the wall next door to it. And you can do really interesting experiments with children. You can say, go knock next door on the wall and listen, or I'll knock here, and you go, and it just blows them away because you would never know this if you hadn't asked them to draw it. So again, this principle is the only way to figure out this cognitive architecture and to see how strangely it's organized is to have someone communicate it in a form. And this is a spatial question. So now scientific models contain exactly these kinds of things if you don't expose them. The ghosts are these missing rules, and we know that models there's lots of rules that we don't have and stuff. So
do you think it's meaningful that he saw the backyard and P.S. it's massive?
I've never seen that before.
Do you think it's meaningful that he included that in his picture of the house?
Oh, absolutely. They had these 2 huge dogs that weren't allowed to come into the house. So, okay. Well, I'm gonna mention that every time now. It's beautiful.
Also, the 2 twins put the house in different orientations, if you notice.
Yeah.
The kitchen's on the upper left.
Yeah.
Here.
Well, maybe I had turned the page the wrong way. Weird things happen when you make PDF files. Okay, so again, now these models infect our daily lives, and we use them all the time. So my favorite example is I'm sitting there typing. I'm always drinking coffee when I'm typing, okay? And the coffee cup is this white thing out there somewhere, and when I don't even look at it. I am typing, and my brain somehow computes how far it is away by looking at the size without me thinking about it. I reach for it, I pick it up, hoping that it's the weight that I expect it to be, and lift it to my mouth. So I have to reach, and usually it has a handle, so my hand automatically knows it has to look for the handle. I'm not thinking about any of this. It uses the model of the cup to orient my hand, grab it, bring it up to my mouth, and take a drink, and then I hope it's the coffee from today and not from 3 weeks ago, which happens sometimes. It's really disgusting. But your brain manages all that. And you know also how it is when you're driving home and your mind's on something else, and you arrive in your driveway and you have no memory of the trip at all. Fortunately, no large animals ran across the road and stuff. But it's because you have a model of that route. You couldn't do that if you didn't know the route. You could do it if you were religiously following your GPS, perhaps, looking at the road. But you couldn't do it. And the reason is because if nothing happens to violate the model, then you can just do autopilot and run the model, okay? But those models are everyday things, and our lives are full of them. The way that we think about objects and how objects ought to behave and how objects interact with each other come from very early childhood experiences. And we're projecting all of that onto this molecular scale, where the time and spatial relations certainly make things much weirder than we can possibly imagine. And we also always depict cells with lots of empty space in it, and things like that. And we just there's so many secret hidden things in our concepts and our basic concepts that we put into science that if you don't look at these things, if you don't know they're there, they're going to mess you up. Okay, so I'll just give you another very simple example. I do a lot of work with an MRI group at our institute, and they were producing these fabulous images. And when you look at this image, it's in grayscale, and your brain sees structures and groups things. So it makes an automatic decisions about what's significant degree of difference in gray and what's not. And you start to see structures. You think, well, this must be connected to this because it's the same color, and this may be something, and this may be something. And this, actually what this is it's a density, it's this bold effect of the amount of water and in the image. So, but maybe our brain takes this image and makes it a little bit simpler in a certain way. So I removed some information from this, trying to keep it looking the same structure. But then I thought, maybe our brain is playing tricks on us, because we look at grayscale things because we look at other things that way. If I were watching a TV show on a black and white TV, I would recognize people. So my brain does all this work, and I have no idea how it works. So what happens if I take the same image and I do exactly the opposite? I tell it, I want to see all the different stages of grayscale, and you get this image. I want to break all of these secret hidden ghosts that are directing how I interpret this, and I get this image. And I showed this to scientists, and they were like, and I asked them, is this meaningful? And they said, yes, it's absolutely meaningful. But you never see it unless you just force your computer to give us much more contrast and colorize and stuff. So that's one example. And so there's all kinds of ways that we make these models. All of them, so you can use math or you can use pictures. And this is a really interesting thing with ghosts. This is one of these signaling pathway things, And every single person here knows that this is very, very different from actually what the situation is like. Because first of all, there's only one copy of everything in here, right? And they're not located in the right places. And this is a scheme that we use for certain things, but it bears no relationship to reality. We know that because we've all learned, we call this the fudge factor. And that is when you know that you're talking in a certain way or making a picture that is very different from reality, but everybody knows how to pack it and unpack it. I think a huge amount of problems with experimental reproducibility come from fudge factors, which lie in describing protocols, experimental, they're everywhere, okay? But this is a simple example. Well, okay, so you can't, these models we have are really complex, and so what should we do about that? Well, here's another one. I mean, this is signaling, okay? And I can't even think about this without drawing it somehow. I mean, I can try to trace my path through little stories here.